Good afternoon. Thank you for joining us for Senior Projects 2020. My name is Edward Mihal, and I will be your narrator for this presentation. We are Project Team 28. We have unofficially named ourselves Engineering Fluorescence. This project was designed for and sponsored by the GVSU Department of Chemistry. I was not alone in building this project. I was joined by three other very capable engineers, Cameron Comer, Caitlin LaBelle, and Samuel Kirk. Our main point of contact and the person that came up with the idea for this project was chemistry professor Dr. George McBain. Our faculty advisor was an electrical engineering professor, Dr. Carl Bacora. Now, let's discuss a few things before we get into the scope and design of our project. The fluorescent lifetime is the time it takes for a fluorescent material to go from the excited state back to the ground state. So this is when we excite a fluorescent material. It starts to fluoresce, and we measure the time it takes for it to stop fluorescing or get back to its ground state, as we call it. This fluorescent lifetime is currently being measured by GVSU students using a fluorescent spectroscopy experiment. Now, what's the problem with this experiment, you ask? Well, the current setup of the GVSU fluorescent spectroscopy experiment is restricted by its analog circuitry, which is only powerful enough to measure fluorescent lifetimes within the microsecond range. Now, this may seem very small, but there are a lot of fluorescent lifetimes that go into the nanosecond and even the picosecond range. Well, you may be asking, well, how do we measure these nanosecond and picosecond fluorescent lifetimes usually then? Well, there are current market solutions that could perform this fluorescent spectroscopy experiment. The machine is called a PMT, which stands for photomultiplier tube. Unfortunately, the PMT has a very high price, which can range well above $2,000, and it has a very substantially large size, which is not very conducive to an educational laboratory environment. So, this is where we stepped in to help alleviate these concerns. So, the goal of our project was to begin the design of a cost-effective fluorescent spectroscopy experiment that could measure fluorescent lifetimes within the 400 to 700 nanosecond range. We were given a set of design specifications, which stated we had to have a system bandwidth of 10 megahertz. This would be an improvement upon the current system, which only had a bandwidth of 10 kilohertz. We were given a budget, which included research and development of $1,000. We had to have an output analog signal peak of greater than 100 millivolts. And our output signal also had to have an SNR, which stands for signal to noise ratio, of at least 25 dB at the peak. Now, we had to make a few changes to our original plan when we first started this project due to the COVID-19 health pandemic. All of our meetings were held virtually. We had to use the enclosure from the previous experiment, which is used to cover our fluorescent material so that we can obtain a signal from it. And we could only develop one single board for testing purposes, whereas previously we would have liked to develop multiple revisions of this board to make sure we had the highest quality of PCB laid out. So, with all that said, let's get to the design process. So, what I have laid out in front of you now is the project design flowchart. It shows each component of our project and how they interact with each other. I'm going to use it to go through each component and explain our design choices to you. And we're going to start at the excitation source. The excitation source is used to excite our fluorescent material so that we can bring it up to the excited state. The excitation source of our project, an LED, was chosen. We chose an LED because it provides plenty of power for the purposes of our experiment. They are easy to purchase in different wavelengths. This is important because fluorescence exerted from a material is on a bell curve in terms of the wavelength in which it is excited by. They have very low cost, so you could purchase many different LEDs of different wavelengths, and they provide a very small spatial footprint, which allows us to maintain a very compact design of the project. So the challenges that come with choosing an LED as your excitation source manifest themselves as quantifying the shutoff time of that LED. Now, you may know the shutoff time of that LED due to its datasheet, but you're never really going to know how it'll work in conjunction with the designed circuit. So, we chose multiple LEDs and ordered them, thankfully due to their cheap price, and we're able to use them all throughout our R&D process before an appropriate LED was chosen for the final design. Now let's move on to our excitation control signal. This signal is supposed to serve as a manual trigger to our excitation source, telling it when to turn on and off. Now this is our excitation control circuit. Now if you look over here on the left with me, we have V1. That is a 15 volt DC voltage source. It is used for control and biasing purposes. The actual triggering comes on the rising edge of V2 over here on the right hand side, which is a 15 volt peak to peak square wave. Now this circuit will provide very sharp spikes of current and voltage to D4, as you see here on the right hand side. This is caused by a pair of coupled transistors we have here in the middle, which use the built-up charge from the capacitors we have here on the left-hand side and shoot that directly towards D4. This allows our excitation source to turn on and off at a very quick rate. So let's talk about challenges faced with excitation control. So we were given a sharp turn on and turn off time requirement due to the nature of trying to capture such fast fluorescent lifetimes. We also had to use TTL logic to drive the signal. We had to use a function generator that could only go up to 3.3 volts peak to peak, which in our design calls for a 15 volt peak to peak signal. Thus, we had to amplify that signal off board and then run it into our test board. And finally, this circuit had to be pretty cheap to reproduce so that we could make it reproducible in the future so that we could have multiple of these fluorescent spectroscopy experiments. So let's take a quick look at the simulation results of our excitation control circuit. So in the blue, you can see our 15 volt peak to peak square wave that we inputted. And in the green here is our output signal running through the LED. And as you can see, on the rising edge of our square wave, we are getting very sharp spikes of current and voltage, which is exactly what we were looking for. And on the falling edge here, you might see a little downward spike. That can be attributed to the reverse recovery time of our LED, and is completely normal. And as you can see, the simulation yields a quick burst of power that can be used to control our excitation source, which is exactly what we were looking for. Now, let's get back to our flow chart here. Let's take a look at the fluorescent material. Now, in the future, when this project is being used as a full-on fluorescent spectroscopy experiment, the fluorescent material could be anything. But for our purposes, we wanted to pick fluorescent material that matched our project specifications in order to verify that the project was functioning properly. So the fluorescent material that we chose for testing is called RuBiPi. It's an organic molecule that has a fluorescent lifetime between 400 nanoseconds and 700 nanoseconds, which allows us to see the very edge of our project specifications. Now let's take a look at the photo measurement device. The role of the photo measurement device is to take the fluorescent light coming off of the fluorescent material and turn it into a low-level analog signal, which we can analyze using circuitry. So for the purposes of our project, we chose an avalanche photodiode as our photo measurement device. A photodiode is just a device that converts light into electrical current, but we chose an avalanche photodiode because it has an average internal gain around 50, low terminal capacitance, and we were able to obtain measurements from a large surface area without much capacitance. Now the reason we want low capacitance in our photodiode is to avoid large spikes of noise in our input, which is obviously something we do not desire. So in conjunction with our photodiode, we had to pick a filter to go with it. We chose theater gel as our filter, and the theater gel is simply placed over the photodiode, and it's used to filter out light from our excitation source. This is because we want our signal coming from the photodiode to be solely comprised of light coming off the fluorescent material and not corrupted by the excitation source light. We chose theater gel because it's cheap, readily available, and works really well for this application. We used the My Color tool on Roscoe's website to determine the best desired filter colors. And it came back with two results. We chose the E105 orange color because it transmits light at 630 nanometer wavelength, which is the peak fluorescent wavelength for RuBiPi. We also could have used the E770 burnt yellow, which would have been acceptable, but not given us the peak fluorescent wavelength. All right, let's take a look at the signal receiver. And the signal receiver is very important because it takes that very low-level analog signal from the photo measurement device and allows us to transform it into a nice large output analog signal that students can interpret and verify the fluorescent lifetime with. So for our signal receiver, we use a dual-stage transimpedance amplifier. A transimpedance amplifier is just an amplifier that can convert current into voltage. The first stage of our transimpedance amplifier offers minimal gain. We do that to reduce the amount of noise that is inputted into the system upon the conversion from current into voltage. And we really use the second stage to amplify our signal into a usable output analog signal. So what are some challenges that come with choosing a transimpedance amplifier? Well, first we had to find amplifiers that offer enough gain to increase the signal to at least 100 millivolts, while also keeping the noise to a minimum to avoid corruption within the system. Second, we had to find proper gain for each stage of amplification in order to avoid oversaturation of the signal. With that being said, let's take a quick look at the amplifiers we used in our design. The first amplifier we chose is the OPA855. It is a wideband, low noise operational amplifier with bipolar inputs for wideband transimpedance. It is suitable for the speed and noise requirements of this project. It offers a stable gain at higher than 7 and a gain bandwidth product of 8 gigahertz, and the low input voltage noise at 0.9 nanovolts over hertz. The second amplifier we chose is the ADA4817-2. It is a high-speed voltage feedback amplifier with FET inputs. It offers stable gain at higher than 2, with the input noise at 4 nanovolts over hertz. And this is our transimpedance amplifier circuit. We symbolize the current coming from our photodiode as a sine wave here, and it is generated from our current source I1 on the left-hand side here. For our transimpedance amplifier, we use the OPA amplifier as our first stage, and that is used to convert the current into voltage. And for the second stage, we use the ADA amplifier, which is used to get the proper gain so we can read our output analog signal. So let's take a quick look at the simulation of this circuit. This is the initial signal, which is coming from our photodiode, which we are symbolizing in this case as a sine wave. Now, this is our signal after running through the first stage of the transimpedance amplifier. And while it seems like it may have gotten a lot of gain, it's not nearly enough in comparison to what we need for our project specifications. But it converted the signal and kept the noise low within the system. Finally, this is the signal after the last stage of amplification. As you can see, this is the stage where we get all of our gain from. And the signal clearly meets the spec of getting 100 millivolts at the peak of the signal. After finally running through the entire program, an analog signal is outputted, which students can look at using an oscilloscope or a graphing program on a computer. Finally, let's discuss the performance of the final product. According to simulations and the initial build, the final design should meet all specifications originally determined at the beginning of the project. A single prototype will be provided to Professor McBain to test for a year before a second revision is made by another group next year. So on behalf of Team 28, I would like to say thank you for joining us this afternoon and hearing about our wonderful project experience. I hope you have a wonderful rest of your day.